Hello everyone, in today's lecture I'm going to talk to you about the signals and basic operations on the signals. So let's get started with signals. A signal is a quantitative description of a physical phenomenon, an event or a process that often has time dependency. Some examples are this audio signal that I provided here. It has time dependency. It can be Dow Jones Industrial Average that you can see in here. It's plotted versus different years. It can be an electrical signal like the ones that you've seen in electrical circuits, like an electrical current that flows in a circuit, or the voltage across a circuit element. Signals we have two types of signals: continuous time signals, or CT, and discrete time signals, or DT. So continuous time signals are signals that are functions of real valued independent variable. So the independent variable, or T, in these signals can take continuous numbers. It's a real valued variable. We usually use the notation of x of t, y of t, and z of t for continuous time signals. I can draw a sine wave as my x of t. This is x of t, and the independent variable is t. So I have a sine wave here, more or less a sine wave, and t can take any real number. So we usually reserve the time variable t for continuous time signals as independent variable, and we use parentheses. Discrete time signals are signals that are defined only at discrete times. So the time variable, which we usually show with n, can take up only integer numbers, discrete numbers that are integer numbers. For these signals, the time variable is the n can only take integer numbers, and we use notations of x of n, y of n, or z of n, and so on and so forth. Right. We reserve the time variable n, the letter n, for discrete time signals as independent variable, and we use square brackets to represent our discrete time signals. All right. So our signals, the signals that we are going to use in ECE 101 are in general complex valued signals. So the value of these signals can be a complex number. A complex continuous time signal x of t is formed by the signal pair of x r of t and x sub j of t. Both of them are real valued signals. So the relationship between these three signals can be given as x of t is x sub r of t plus j times xj of t. In this expression, j is square root of -1. Okay. Similarly, a complex discrete time signal, or x of n, can be represented as x sub r of n plus j times x sub j of n. In this expression, both x sub r of n and x sub j of n are real valued discrete time signals. You're going to see signals like this throughout the course. So basic notations, just for review: the set of integers can be represented using Greek letter z. These integer numbers are -2, for example, -1, -100, 0, 100, 200, and so on and so forth. The set of real numbers are represented with Greek letter R, and complex numbers are shown with Greek letter C. These complex numbers can be written as a plus b times j, in which a and b are both real numbers, just similar to what we had for the case of complex signals. So this representation, x equals to a plus b times j is the Cartesian coordinate representation. We can also show complex numbers in polar coordinate, for example, by writing it in this format. And the Cartesian and polar coordinates, the representation in these coordinates are related. So in this polar coordinate, r, if you write x as r multiplied by e to the j theta, r here is square root of a squared plus b squared, and this a and b are these a and b shown used in the Cartesian coordinate. Theta in this expression here is e to the j theta. Theta is tangent inverse of b over a, and b over a are used in the Cartesian coordinate. We use Euler's formula to go back and forth between Cartesian coordinate and the polar coordinate, and you're going to use Euler's formula throughout the course. All right. Now that we are done with the definitions of signals and looking at discrete time signals and continuous time signals, let's look at some basic operation on these signals. Okay, the first operation that we're going to look at is time shifting. So time shifting on x of t is transforming x of t to x of t minus t naught. This is for the continuous time signals, and for discrete time signals is building x of n minus n naught from x of n. In these expressions, t naught is a real number and n naught is an integer, because x of n is only defined for integer values of n, and in x of t, t can take up any real value. If t naught is a positive number or n naught is a positive number, this operation is called, or this time shifting is called delay. And if t naught is a negative number or n naught is a negative number, this operation is called advance. All right, so let's look at an example of this time shift for a given signal x of t that's plotted in here. All right, so we have x of t, and we would like to sketch x of t minus 1. Whenever you have an operation for a signal, it's a good idea and it's recommended to first name the transformed signal something else. Like, for example, here I'm going to name it g of t, and I'm going to say that g of t is equal to x of t minus 1. So now I want to plot g of t, and this is the plot of g of t as a function of time. All right, and I know this g of t is the shifted version of x, and I can find g of t by calculating x of t minus 1. X of t minus 1 is the shifted version of x of t by 1 point to the right. Basically, it's the delayed version of x of t. All right, so I can plug in numbers point by point for t and then calculate g of t. So let's give some numbers here. So for g of t at t equal to negative 2, so I can say g of t at t equal to negative 2 is the same as g of negative 2, and that's equal to x of negative 3. All right, so I'm looking at my graph of x of t, and I want to find the value of x of t at t equal to negative 3. And if I look at here, x of t at t equal to negative 3 is 0. So g of negative 2 is 0. How about g of t at t equal to negative 1? This is going to be equal to g of negative 1, and that's going to be equal to x of negative 2. That's also equal to 0. I'm looking at the graph of x of t, and at t equal to negative 2, x of t is equal to 0. So again, I have a 0 here. So between negative 2 and negative 1, g of t is equal to 0. So moving on, at t equal to 0, g of t at t equal to 0 is equal to g of 0. That's equal to x of negative 1. So the graph of x of t at t equal to negative 1 is discontinuous. That means to the left of t equal to -1 in here, to the left of this point, x of t is equal to 0, and to the right of this time point, x of t is equal to 1. So I expect to see similar pattern for g of t. In other words, to the left of t equal to 0, here in the graph of g of t, I should have g of t equal to 0. And to the right of t equal to 0, I'm going to have g of t is equal to 1. All right. So moving on, at t equal to 1, I'm going to have g of t equals to 1. At t equal to 1, again, g of t is going to be equal to 2. At t equals to 3, x of t is discontinuous. It's going to happen to g of t as well. So expect to get it equal to 2. And it's going to go down here to the right of t equal to 3. So I'm going to have g of t is equal to 0. So this is the shifted version of x of t, and I plotted it. The next transformation is time reversal. It's defined as transforming x of t to x of negative t for continuous time signals, and transforming x of n to x of negative n for discrete time signals. Basically, it is flipping over y-axis. It's the time reverse version. It's basically building the time reverse version of the original signal. Let's practice it in here. The only thing you need to do here is to flip the given signal, or you can give the new signal some values, some time points, some values for t, and draw the new signal. Again, because we have a transformation here, we are going to name the transformed signal something else other than x of t. So I'm going to name the new signal g of t. That's going to be equal to x of negative t. All right. So I'm plotting g of t in here. And I expect to sketch the flipped version of this one with respect to the y-axis. So at t equal to +1, I expect to get something like this. All right, -1 in here, -2 in here. I expect to get it here like this, and then like this, and then like this. This is 2, this is 1, good, and this is my graph of g of t. I can plug in different numbers for g of t and then find the corresponding value of that point in the graph of x of t, and then use those time points to finish the plot of g of t. Or in this example, it was simple example. It was a simple example, so I was able to plot it. The next transformation is time scaling. For continuous time signals, time scaling by a factor of a, where a is a positive number, is defined as transforming x of t to x of at, or building x of at using x of t. And in this transformation, a is a positive number. If a is greater than 1, this time scaling is called decimation. Basically, you're squeezing the signal. And if a is a positive number between 0 and 1, this transformation is called expansion, or enlarging the signal. Here's an example of decimation for a signal x of t as given below. If I want to build x of 2t, I can build it from x of t. I'm going to name it g of t. I'm going to write g of t is equal to x of 2t. And I can plug in some numbers for g of t to plot it. So g of t for t equal to 0, let's write it in here. G of t for t equal to 0 negative. That means for time point close to 0, but slightly less than 0. That's equal to x of t at time point slightly less than 0, or for example, negative 0.0001, something like that. It's a number close to 0 but slightly less than 0. The value of x of t for this time point is equal to 1, and g of t for t equal to 0 positive. That means g of t for a time point close to 0 but slightly greater than 0. That's equal to x of t for a time point equal to a number close to 0 but slightly greater than 0. That is equal to 2. For example, in here I have 1 and 2, so g of t is 1 and 2. At g of t at t equal to 0.5 is equal to x of 2 times 0.5. That's equal to x of 1, which is maybe negative 0.5, negative 2 times 0.5, and this is negative 1, and I have it in here, and that's equal to 1. So let's see what we did in here. At t equal to negative 0.5, I have x of negative 1. Okay, so it's here. Negative 0.5, I have x of t that's equal to 1. Again, g of t at t equal to negative 1 is x of t at t equal to negative 2, which is again the discontinuous point, and that's going to give me this point in here. All right. You can complete this graph by plugging different numbers for time points for the graph to find g of t at that time point using the graph of x of t. All right. Here's an example for finding x of t over 2 using the graph of x of t. Okay, so I'm going to name the signal something like g of t again, equals to x of t over 2. Okay, it's going to be the expanded version of x of t. So g of t is going to be expanded version of x of t. Basically, what's happening is expanding x of t, expanding the signals on the time point by fixing the middle point or fixing the value of graph at t equal to 0. In other words, the value of g of t at t equal to 0 is going to be the same as the value of x of t at t equal to 0. So it's like you're holding the middle point, fixing the middle point on your graph, expanding the graph or enlarging the graph, in this case, doubling the x-axis. I'm plotting g of t here. What happens for at t equal to negative 2 for x of t is going to happen here in g of t for t equal to negative 4. And then I have to the left of t equal to negative 4, g of t is 0. To the right of negative 4, I have g of t equals to 1. All right, this is 0. This is negative 2. Okay, in the right side, I need to expand it. So what happens at t equal to 2 is going to happen at t equal to 4 in here. And what happens at t equal to 4 here is going to happen at t equal to 8. So it's going to come to be equal to 2. And then at t equal to 8, it's going to decrease down to 1. After t equal to 8, g of t is going to be equal to 0. So this is the expanded version of x of t. If you have an audio signal, the process of expansion means slowing down the signal, and the process of squeezing means speeding up the signal. Right? For a discrete time signal, and an integer factor m when m is a positive number greater than or equal to 1. The decimated signal is defined as yd of n, which is going to be equal to x of mn. Here is an example for m equals to 2. You have x of n and yd of n is going to be equal to x of 2n. So for n equals to 0, yd of n is equal to x of 0. For x of n at n equal to 0 is 6. Yd of n at n equal to 0 is going to be equal to 6. Yd of n at n equal to 1 is yd of 1, and that's equal to x of, using this relationship, it's equal to x of 2. That's going to be equal to 4. So I have this 4 in here for n equal to 1. And the same goes for the rest of it. For n equal to 2, yd of n at n equal to 2 is x of 4. So I come here for x of 4. X of n at n equal to 4 is 4, and then I plot it in here. We usually use stem plots for plotting the discrete time signals. So moving on, for n equal to 3, yd of n at n equal to 3 is x of 6, and x of n at n equal to 6 is 0. So yd of n at n equal to 3 is going to be 0. Let me erase these 2 points so we don't get it confused. So we don't get confused here. So the values of the signal yd of n at all of these time points is equal to 0. Similarly, to the case of continuous time, for an integer value greater than or equal to 1, the discrete time expanded signal E of n is defined as xn over L when n is an integer multiple of L. However, for time points that are not integer multiples of L, y sub E of n is going to be equal to 0. That's the difference between expansion for continuous time and discrete time case. For continuous time, signals are defined for all values of t or continuous values of t. But for the case of discrete time signals, the time variable can take up only integer values. Here's an example of the expanded version of x of n by a factor of 2. For at n equal to 1, x sub e of 1 is equal to x of 1 over 2, which is not defined. So I'm going to replace y of 1 as 0. I'm going to replace 0 for y sub e of 1. And when you have a combination of operations, you're dealing with both time shifting and time scaling. The order in doing these operations matters. So the recommended method is to first do the time shifting, then doing the time scaling. So we first need to define a new signal. That's the time shifted version of the original signal, and define the second signal, which is the scaled version of the or the signal defined in step 1. So this is first time shifting and then scaling. If b is a positive number, then this time shifting is called delaying. So we first delay. If b is positive, basically we first delay the signal, then time scale it. The second method is to first scale it, then do the time shifting. But the operation is going to be a little different, so you need to keep an eye on how you perform this operation. So as soon as I define v of t equals to x of at, y of t is going to be equal to v of t minus b over a. So if I have v of t in here defined for t, that's equal to x of a multiplied by t. If I want to find v of t minus b over a, I'm going to come here. I'm going to replace this t with t minus b over a, and then I'm going to come here. Whenever I see t, I'm going to replace this t with t minus b over a. So v of t minus b over a equals to x of a multiplied by t minus b over a. that's going to be equal to x of at minus b. So that's the transformation that we were looking for. And on top of that, this method is not recommended for discrete time signals because in the process of decimation for the discrete time signals, you are going to lose some samples. So ultimately, the result of this transformation, if you use the second method to perform the combination of transformations, the combinations of transformations might not be the correct answer that you're looking for. So the recommended method when you're dealing with combination of transformations is to do the time shifting first, then the scaling. So let's look at this example of doing this combination of transformations, including the time shifting and scaling on this given signal x of t. We would like to plot x of negative t plus 2. I'm going to go with the recommended method of time shifting first and then scaling. So I'm defining a new signal v of t as x of t plus 2. Then the next signal is going to be g of t. That's going to be equal to v of negative t. Ultimately, it's going to give me x of, I see t in here, and I'm interested in finding, I have v of t, and I'm interested in finding v of negative t. So I'm going to, I see t in here, so I'm going to plug in negative t and x of t plus 2. So that's going to give me x of negative t plus 2, right? Okay, so that's, and basically I verified that this process is going to give me the correct answer that I'm looking for. So now I'm plotting v of t. Let's prepare the axes. So this is my v of t. V of t is the shifted version of x of t by 2 points to the left, and that's gonna give me so what happens in x of t at t equal to negative 1 is gonna happen in v of t at t equal to negative 3. So I'm gonna label this one. So it's gonna v of t is going to be 0 at t equal for time points less than negative t. So it's gonna be equal to 1 immediately to the right of t equal to negative 3, and it's going to continue until t equal to 1 for x of t. So that means it's going to continue for v of t until t equal to negative 1. All right, so that's going to come to here. And then at t equal to 0, I'm going to see the same thing that I see in x of t for t equal to 2. So it's going to go to t, v of t equals to 2, and this is 1. All right, and then it's going to go to 0. Okay, so I shifted this signal by 2 points to the left, and now I'm ready to plot this the inverted version of v of t. So now I know that g of t is the inverted version of v of t, so it's the time reversal operation. So I'm going to label this one as 1, 2, 3, and this is going to be 0. So this is 2, this is 1. So it's going to come here. It's going to extend to t equal to 3. It's going to go to 0. This is going to go to 0. And that's it. So basically this is g of t, which is equal to x of negative t plus 2. Thank you for watching. We looked at the signals, definitions of signals, and we reviewed some basic transformations on the continuous time and discrete time signals.